Bismillahirrahmanirrahim. So in this video we are going to continue from where we left in the last lecture last week. So just to recall, we looked at the log-based protocol and we saw that even with the log-based protocol there is a possibility that if the first transaction were to have a shared lock on A, then read A and then unlock A, and maybe there's a second transaction that reads and writes A in between, and this transaction then goes on to have a shared lock on B and then read B and then unlock B. So even though that when we are reading B we are having a lock and an unlock, when we read A we had a lock and an unlock. However, in between when this was unlocked, A was unlocked, if another transaction modifies the value of A, there's a possibility that we end up with the wrong answer. It means that we have a dirty value, or we can have certain other issues with this kind of a log-based protocol. So to deal with that, we propose what is known as the two-phase locking protocol. So in the two-phase locking protocol, there are two phases. The first phase is the growing or the locking phase, and the second phase is the unlocking or the shrinking phase. So in the growing phase, what happens is that a transaction applies lock. It could be either a read lock or a write lock on the desired data items one at a time. So whenever you encounter, if you have to modify the table A, you acquire a lock on A, and then next you have to modify B, then you acquire a lock on B. However, you do not release the lock. You see, the problem here was when we had a lock on A, we read the value of A and then unlock A so that A becomes available for others. In the two-phase protocol, there is no unlock here. So at the time the transaction is growing or in the locking phase, you successively acquire new locks on whatever data you are trying to modify or read. So if you are reading, you acquire a read lock. If you are trying to modify something, you acquire a write lock. However, once you have read the data, you don't unlock it. You keep the lock for yourself, and only when you are done all the modification, then you move on to the second phase. That's why it's called the two phase. So the first phase is the locking or the growing phase, and the second phase is the unlocking or the shrinking phase. And the shrinking phase is naturally when you start unlocking all the values that you have. So a transaction unlocks its locked value data items one at a time, and a new lock may not be acquired in this phase. So in the growing phase you keep locking but you don't unlock. In the shrinking phase you keep unlocking and you don't acquire a new lock. So the protocol assures serializability. It can be proved that a transaction can be serialized in the order of their lock points. That is, the point where a transaction lock is acquired. So from that point you can have a serializable. It can be proved, and we see that in a few slides how we can ensure that this will happen. So let's look at this example. We have two transactions, T1 and T2. And there are 10 different timestamps where some operation occur in either T1 or T2. So we can see here for the first transaction you have a shared lock on A, an exclusive lock on B, and then unlock and unlock. So from step 1 to step 3, 1, 2, 3, this is the going phase. You are acquiring locks, and then once you have finished whatever you're doing, then you start unlocking the data. There is no new lock in the rest of the transaction after step 3. So the lock point is at 3. So this is where you have the maximum number of locks, and after that you are just going to keep unlocking. And for the shrinking phase is from step 5 to step 7. And for the second transaction, the growing phase is from step 2 to step 6. And the shrinking phase is step 8 and 9, and the lock point is 6. It means that at step number 6 you have acquired the maximum locks that you needed. So what happens if you have something like this? You have three transactions, T1, T2 and T3. So T1 acquires an exclusive lock because it wants to write. It requires an exclusive lock on A, and then it reads A and then writes A. And then for B, it has a shared lock on B. It reads B and then unlocks A and unlocks B. So this is the growing phase, and this is number 6 is the shrinking phase. So you can see that transaction T2 and T3 are doing nothing at that time. So after the step number 6, transaction 1 is now more or less complete, in the sense that whatever we wanted to do, whatever operation we wanted to do, we have already done that. So now transaction 2 starts, and then it have A in an exclusive lock. So A has already been written here, and the table has been unlocked, so that's fine. You can acquire an exclusive lock here. Read A, write A, and then unlock A. And then after this is finished, transaction T3 have a shared lock on A because it just wants to read. Now this is fine because you had a lock and then you read and wrote and then you have an unlock. What if this transaction fails? Because we said that a transaction is completed when we encounter the word commit, the keyword commit. After commit has successfully executed, that is when we say the transaction is complete. So even though we have unlocked everything here at number 6, it's not complete until we have a commit statement. So what if that commit fails? Maybe there's a loss of electricity, maybe the disk has gone haywire or something like that. Maybe there's a loss in connection in between, and you fail to commit. It means that this transaction is going to roll back. So if this fails and it's going to roll back, so if it rolls back, then these two transactions are also going to roll back. So read A in T2 and T3 will denote a dirty read because write A in T1 has occurred. So because this has occurred and we read the new values of A here and here, and at the end when if you roll back, it means that this write A never occurred in the first place. So this and this read were inconsistent with the original value of A. So in this case, it's a bit time consuming, there's a lot of effort wasted, but at least it is in a consistent state. So if T1 aborts and it fails to commit, it's going to have a rollback, and if this rolls back, then the T2 and T3 will also roll back. So the two-phase locking protocol is further divided into two categories. Not even a category, it's like two possibilities of the two-phase locking protocol. One is the basic phase and the second is the conservative phase, and they differ in how strict they are in acquiring the locks. So in the conservative locking protocol, it prevents deadlock by locking all desired data items before a transaction begins execution. So if you have something like this, it's not going to have a lock unlock, it's going to acquire all the locks. So lock on A and lock on B will occur at the same time. If you can't lock everything that you need, the transaction won't start. In the basic version, the transaction locks data incrementally. So when you encounter A, you have an exclusive lock on A, and then you encounter B and you have an exclusive or shared lock on B. But A and read A and write A would have been executed before you acquire a lock for B. And this is helpful because by the time you are doing read A and write A, lock of B is available. In fact, B is available, it's free for anybody else to use during that time. So maybe somebody will read and write B before T1 finishes writing A. Maybe A is a very large table and it takes some time to write A, and you don't want to keep B exclusively for yourself, and you want to let other people work on B if they can. And so in the basic version, lock A, then read A, then write A, and then lock B. In the conservative version, lock A and lock B will be acquired first, and then read A and write A will start. So all the locks that you need will be acquired at the start, and then the transaction will begin. Otherwise, if you can't acquire all the locks that you need, the transaction won't begin. So a more stricter version of the basic algorithm where unlocking is performed after a transaction terminates, and this is most commonly called the two-phase locking algorithm. So in fact, the two-phase locking algorithm ensures that you are going to unlock them only after you have finished all the operations. So as we said that it can guarantee that there is going to be, the protocol assures serializability. We mentioned this, that you can guarantee that it's going to be serializable. How? Let's look at this example. So in this case we have transaction T1 and T2. So you have a read X and then X equal to X minus 5, and then write X and commit. So before you start reading X, you need to acquire a read lock on X. So while you have a read lock on X, another transaction T2 simultaneously starts. It also wants a read lock on X, and because this is a read and a read, so it will be allowed. There is no issue. This is going to also have a read lock on X. Now when you come to writing the X, because you have modified the value of X, before you write you need to acquire a write lock, which will not be possible because T2 has already acquired a read lock. So just recall that read and read is possible, read and write, write and read, or write and write, these three combinations are not possible. Only read and read is possible. So in this case, because there is already a read lock by a second transaction, it means you cannot have an exclusive lock for yourself, because exclusive means you are the only one that have the lock and nobody else has any kind of lock, whether read or write. So this is not going to be possible, and when you want to execute this, you want to finish the second transaction, this is also not going to be possible because T1 already have it and a read lock, and it has not unlocked X. So this is also not going to be possible. So it's going to prevent this writing from happening, so you don't have to deal with a lost update, because otherwise this write X would have been lost with the new value. So whatever T1 have written for X, that value would have been lost, and because T2 comes later, so whatever it writes for X, that would be the updated value present for the table X. So uncommitted update also cannot happen with the two-phase locking protocol. So in this case we have read X, X equal to X minus 1, and write X. So everything, all the operations are done, we don't have anything in between. Once you have written, then you have read X, X equal to X plus 5, and write X. So in this case you have a read lock on X, that's okay, and then you have a write lock, and because nothing was happening here, that's also fine. And then you go wait till T1 releases the write lock, and that won't be released until after it had committed. But because it doesn't commit, it rolls back, it means that this will undo, and then the locks will be released. So in this case the locks are released only after a commit or a rollback. So because of that, you can't have an inconsistent value, because if it rolls back, it means this write never happened, and this X equal to X minus 5 never happened, and X was in its original value. You have a rollback, and then the X that was locked for writing is now released, and if it's released, then T2 can continue. Otherwise it's going to wait for T1 to release the lock, and the lock will be released after the rollback. So inconsistent analysis also cannot happen. So we cannot have a lost update, we cannot have an uncommitted update, and we cannot have an inconsistent analysis. So if in this case we have T1 is read X, X equal to X minus 5, and then write X, and then the second transaction comes read X, read Y, sum equal to X plus Y, then read Y, Y equal to Y plus 5, and write Y. So in this case, before you read X, you need to have a shared lock on X, and then before you write, you need to have a write lock on X. So once you have the write lock on X, you cannot have a read lock, because only read and read is permissible. Read and write, write and read, write and write, the three are not permissible. So once this is in an exclusive lock with T1, you cannot have this, and this lock will continue until a commit or a rollback. So it waits till T1 releases write locks on both X and Y. So in this case, if it was a basic algorithm that you are doing, you only have a read lock on X. If it was a conservative, then you have a read lock on X and Y both, because we said that all the locks are required at the beginning. So in this case, you can see that inconsistent analysis is not possible. T2 cannot execute until this finishes, has the commit, and releases the locks on X and Y. So however, deadlock is still possible. And how is it possible? It's possible because, in fact, what's a deadlock? A deadlock is a set of processes, or a set of processes is a deadlock if each process in the set is waiting for an event that only the other process in the set can cause. So T1 is waiting for T2 and T2 is waiting for T1. So as an example, you have you have two different schedules. So X1 is having a lock on A, and X2 is going to have a lock on B. So the first transaction have a lock on A, and the second transaction have a lock on B. Now the first transaction is waiting for B, and the second transaction is waiting for A. So this is in a wait state because it wants T2 to release B, and T2 is in a wait state because it wants T1 to release A, and they're going to keep waiting in an infinite loop, and nobody is going to let go. So just going to check whether the data A or B is available. No, it's still locked. Go back to sleep. After some time, wake up again. Check again whether the lock has been the value have been unlocked or not. No, and then go back to sleep, and so on. So it's going to continue waiting in an infinite loop, and that is a deadlock. A is waiting for B. T1 is waiting for T2 to release B, and T2 is waiting for T1 to release A. So the deadlock may occur. T1 is waiting for B, and T2 is waiting for A. And we can see that this is as we saw in the previous lectures. This is, if you can see using this precedence diagram, this is a cycle. Therefore, drawing the precedence graph, you may detect the loop. So deadlock is also possible in a two-phase locking protocol. And also two-phase locking may also limit the amount of concurrency that can occur in a schedule, because now you have to acquire all the locks, and then the other one is waiting because they can't have the lock. So it ensures that there is no dirty update, there is no lost update, there is no anomaly, but it means that the scheduling cannot be as concurrent as we would like it to be. So what happens if we do encounter a deadlock? How do we resolve that deadlock? Now there are four conditions that can happen for a deadlock to occur. So the first is mutual exclusion condition. So each resource assigned to one process or is available. Hold and wait condition. Process holding resources can request additional resource. No preemption condition. Previously granted resource cannot be forcefully taken away. And circular wait condition. Must be a circular chain of two or more processes. Each is waiting for the resource held by the next member of the chain. So if I can either have something like this, T1 and T2. So T1 is waiting for T2 to release something, and T2 is waiting for T1 to release something. Or I can have T1 and T2 and T3. T1 is waiting for T2 to release something, T2 is waiting for T3, and T3 is waiting for T1. So this is also a cycle, and this is also a deadlock. Not all cycles are deadlocks, but a cycle can help you identify if it's a deadlock or not. So what happens if a deadlock does occur? How do we resolve that? Now for that, there are three ways we can do. The first one is the deadlock prevention. It means we don't let the deadlock occur in the first place. So if there is no deadlock, then we don't have anything to solve. And the way to do it is that a transaction locks all data items it refers to before it begins execution. So this is the conservative protocol. This way of locking prevents deadlock, since a transaction never waits for a data item. It will have everything at the beginning, or it will release whatever it has. So it's not going to have a part of the data and wait for the rest. It will try to acquire all the data it needs. If it gets it, fine, it will start the execution. If it doesn't get it, maybe it needed 5 tables, it was able to acquire a lock on 3 of the tables and not 2 of the tables. It will wait, but it will release the 3 tables. And so if the other one was waiting for the 3 tables, they can have the 3 tables because this transaction has released. It will wait some time, and after some time try to grab all the 5 tables again. If it's successful, it will go ahead. Otherwise, it will release whatever it has grabbed and then go back to waiting. So this is not very practical, because the first thing is that to have all the tables I need, if I need to do many transactions and I'm just have acquired all the tables for me, it means all the other transactions will be starving. They won't have access to the data they need. And similarly, if there are a lot of transactions, I cannot start my transaction until I get all the tables in an exclusive lock for me. And if I can't get those, it means I'm going to keep waiting forever. So this is not a very practical solution. So what happens is that we do allow the deadlock to happen, and we try to resolve it. So first is the deadlock prevention, then the deadlock avoidance. The avoidance is there are many variations of the two-phase locking protocol. Some avoid deadlock by not letting a cycle to happen. So as soon as you see a cycle, you can break it. This is as soon as the algorithm discovers that blocking a transaction is likely to create a cycle, it rolls back the transaction. So you keep incrementally acquiring the locks. However, if you see that you are going to have a deadlock scenario, and that is detected by a cycle in the graph, then you roll back and you release the element so that the other transaction can finish before you can acquire yours. And for that we have the wound, wait, and the wait die algorithms, which we will see in the next slide. And the third type is the deadlock detection and resolution. So in this case, the deadlock has been detected and we are trying to resolve it. In this approach, deadlocks are allowed to happen. The scheduler maintains a wait for graph for detecting cycle. If a cycle exists, then one transaction involved in the cycle is selected and rolled back. So this is an example of the deadlock avoidance. A wait for graph is created using a lock table. As soon as a transaction is blocked, it is added to the graph. So if a transaction is blocked, it means that it's waiting for something. It's added to a table or the graph, and whatever it's waiting for, it's mentioned. When a chain like Ti waits for Tj, Tj waits for Tk, which waits for either of Ti or Tj occurs, so there is a cycle, then we are going to break that cycle. So the two rules we said, wound, wait, and wait die algorithm. Let's see what they do. The wait die rule: if Ti requests a lock on a data item which is already locked by Tj, so I is requesting the item is already locked by Tj, then Ti is permitted to wait if the timestamp, Ts is for timestamp, if the timestamp of Ti is less than the timestamp of Tj. If the timestamp of Ti is greater than Tj, then Ti is aborted and restarted with the same timestamp. Timestamp means the time the transaction starts. So if T1 start here, so this is where T1 starts, and T2 starts later. However, at some point you see that the timestamp of Ti is less than Tj. Yes, because if you are having the time in this fashion, this started much earlier and this started much later. So the timestamp of T1 is earlier than a Tj. So let us call it Ti and Tj. So if Ti has a timestamp earlier than Tj, it's going to wait. Otherwise, if it started later, maybe if ti started here, then ti will be aborted and it will be restarted with the same timestamp at the time which it is aborted. If timestamp of ti is less than tj, which is the case here, ti started before, then ti waits, else it will die. The transaction will be aborted. It is non-preemptive. It means that ti never preempts tj, and therefore it prefers younger transactions. So if it's an old transaction, you can wait. Otherwise, the younger transaction will be given preference. The wound wait rule says that if ti requests a lock on a data item which is already locked by tj, then ti is permitted to wait if and only if the timestamp of ti is greater than the timestamp of tj. If it is not the case, if ti is less than tj, then abort tj and lock is given to ti. So in this case, if I have ti, so again this is my time. If I have ti over here and I have tj over here, and ti is permitted to wait, so at some point this required maybe a lock on x, but this lock was already provided by to tj. It means that j has already locked x. However, ti started before. So if the timestamp of ti is greater than tj, then it's going to wait. If it started later, then it's going to wait. Or in this case, since it started earlier, it means that tj will be aborted and it will be assigned to ti. So if timestamp of ti is less than tj, then tj is aborted and the lock is assigned to ti. Is here we have an assigned to ti. So in this case, if ti is less than tj, then tj is wounded, else ti waits. So if this started later, it means it is wounded, it's going to be abolished. Otherwise, if this started later, then this is going to wait and let tj finish whatever it's doing. So this is preemptive. Preemptive in the sense that if ti requires the lock and it started earlier, it's going to preempt, it's going to stop, forcefully stop transaction j and give the lock to I because I was in the queue before j ever occurred. So this prefers older transaction. In this case, there is no preemption. Even though ti started earlier, if the lock is with tj, it is going to remain with tj. In this case, tj is going to be aborted and the lock will be given to ti. So this favors the older transaction, this favors the younger transaction. So these are the two ways we are going to avoid the deadlock whenever we detect a cycle. And you can see here that this lock x has been acquired by j and it's wanted by I. So if that's the case, then whenever you encounter that, if depending on whichever methodology you are using, either you are going to let it wait or you are going to abort it. So in this case, even if you let it wait, in this case, if ti is less than tj, then ti waits, else ti dies. So if it was at a later stage, then ti will be aborted. So in summary, locking all potentially conflicting objects at transaction start reduces concurrency. So because we are going to have all these locks, and if one is able to lock and the other cannot lock, it means it cannot run simultaneously. So there's a lot of weight involved. So weight, I'm talking about this weight, not how heavy it is. So also some of the transactions object may be determined dynamically. So at runtime we will see whether you can acquire or not, and whether the transaction will be aborted or not. and whether it's going to await condition. So usually some form of two-phase locking protocol is used. The simple lock protocol is normally not used. The two-phase is used. Either you use the non-strict version, so of the phase of acquiring locks are acquired as the objects are needed, and the phase of releasing, it is released once all the executions have complete. It ensures serializable execution, however is subject to deadlock and cascading abort. So if A aborts, then all the others that had acquired values that this has released. So if I had T1, T2 and T3, what this cascading abort means that if I had a lock on X here and then unlock on X, and then this had a lock on X and did something, if here I roll back, then this is going to roll back and this is going to also roll back. So this is a cascading abort. If this is aborted, it rolls back, then all the others also have to roll back. In the strict two-phase protocol, two-phase locking protocol, phase of acquiring is as above. However, it holds all the locks and releases after commit, and that enforces isolation, and therefore it prevents cascading abort. So if I have a lock here, this unlock will not happen at this point. Instead, either I commit or roll back, the unlock will happen at a later stage. So if an unlock happens here, it means this could never have happened. This transaction will start here. So if I roll back, doesn't matter, this is still waiting, it has done nothing. So if I roll back, only this transaction will be rolled back. T2 couldn't have started because there was a lock, and T3 can't start because there is a lock, and the unlocking will only begin when you roll back or commit, and so you cannot have something in between. So with that, we finish with the concurrency. So I hope it's clear, the transactions, how you use the precedence graph to look at what is serializable or not, and then the locking protocol and the two-phase locking protocol, and how a deadlock can still occur, and how you are going to resolve the deadlock by using either the wait die or the wound wait strategy. So that is it about the serialization and concurrency about transactions in databases, and this is something that is used a lot. So whenever you go to the ATM machine, a lot of people are trying to access the ATM machine at the same time. So the bank ensures that such a locking protocol is being implemented and the database is in a consistent state. Same goes for an online shopping mall, Amazon, Daraz or something like that. Everywhere that you can imagine a concurrent access, such a locking protocol is in place. So with that, we end this lecture. If you have any questions, you can ask me either on MS Team in the comment section or during the question answer session. So thank you.